Good afternoon and good morning to those in the Mountain and Western time zones. Welcome to our HµREL Corporation webinar. My name is Matthew Shipton, Head of Sales and Marketing for HµREL Corporation. I'm joined by my colleague, Dr. Eric Novick. Dr. Novick is our HµREL Corporation's Chief Technology Officer. Dr. Novick has an extensive background in tissue engineering and co-culture development. He's done a great deal of work optimizing the HµREL Corp system. Today's webinar is broken up into several parts. First, we'll talk about the HµREL Corp system itself. Next, we'll talk about using our systems for a variety of drug metabolism and toxicology, in vitro toxicology applications. Lastly, we'll touch on our HµREL flow system, which is currently in development. For those of you who are not familiar with webinars, there is a panel on your right-hand side. Should you have any questions throughout the webinar, please feel free to type those in. We'll try to answer as many of those at the end of the presentation as we can. If for whatever reason we do not get to your question or you have additional questions, our contact information will be at the end of the presentation. We will also follow up with those that asked questions which we were unable to answer at the end of the presentation. With that said, I will turn it over to Dr. Eric Novick.
All right. Hello, everybody, and thank you, Matt, for the introduction. Just to give you a little bit of an overview of what HµREL does, we make hepatic cell-based co-culture models in 4 species. We do it in humans, in dogs, in rats, and in primates. And more recently, we've begun to characterize human-pooled donors and hepatocytes. At HµREL, we focus on practicality and convenience as well as excellent function and scientific merit of our products. The plates are delivered by air overnight. They come ready for use after a brief acclimation period, which can be anywhere from 4 to 24 hours. And for those of you that like to contract some compounds out, we have contract services options available for you. The co-culture model comes in any plate format that you'd like. We go from 6 well all the way to high throughput 384 well plates, again delivered overnight by air to your door. Just to give you a snapshot of the different cells that we have and what they look like from left to right, we have the HµREL human, primate, dog, and rat. The co-culture hepatic models are primary cryopreserved hepatocytes cultured together with a stromal non-parenchymal cell type. These cells are characterized by us for long-term function and optimized for a window of stable function in the customer's hands. Need a stromal cell or a co-culture. Cells look great, and the picture on the left shows 2-day monocultures of rat primary hepatocytes after being freshly isolated. You can see the beautiful islands, the way the cells connect, the nice nucleus, and then after 4 days in monoculture, what you see is a degradation in the overall morphology and function, and this prevents a researcher from doing long-term studies. And one way to get the cells to last for the 14 or 21 days that one might need to do the work is to do it in co-culture. And you can see that on the picture on the right. The 14-day co-culture hepatocytes look very similar to the 2-day monoculture, and in fact function even better. So if you look at the graph on the bottom, you see the gray bars where the single-cell cultures are decreasing in function over time, and the blue bars are increasing over time, stabilizing right around day 7 to 9. What we do at HµREL is we identify a window of stable enzymatic activity where we ship the cells out and the customer can have stable function enzymatically over 14 to 21 days. So when we characterize these cells, we go all the way from the first day of seeding out to day 35 of seeding. You can see that in the chart on top. This happens to be an example of the HµREL human product, and we're assaying for CYP3A4 function by measuring the formation of 1-hydroxymidazolam. And you can see that right around day 6 to 7, the enzyme begins to stabilize and stays functional for at least 25 days. So when we refer to day 1 of customer day 1, it's really day 7 of culture, where we plate our cells on day 1 the hepatocytes with the stromal cells. We give them 7 days of stabilization in our labs, in our incubators, and then on the 7th day we pack up the cells and ship them to your door. So that's the graph on the bottom highlighting what is in that red square. You can see that from customer day 1 all the way out to customer day 18, you see very stable and highly functional 3A4 cytochrome P450s. So what you get is 2 weeks of stable culture, and that's usually a long enough window of time for most tox and DMPK applications. All the data that I'll talk about from here on out will say day 1, and that would be customer day 1. This is a measure of the window of stability in multiple SIPs in 3 separate single donor human lots. Looking from on the top from left to right, you have 1-hydroxymidazolam formation as a measure of 3A4, dextrofan formation as a measure of 2D6 activity, and on the bottom you have 4-hydroxytolbutamide formation as a measure of 2C9 activity. Each specific graph has 4 different colored bars on it, and that represents the 3 different human donors that we are assaying. And what you can see is that, number 1, the donors are different. So every donor has its own enzyme activity. And the second thing that you see is inside that donor, for that individual donor, you have very stable function for 18 days from when a customer would receive the cells. This is some enzyme activity generated for one of our human donor lots by Bristol Myers Squibb. This is data that's generated at customer day 1, customer day 2, 3, and 4, and that's symbolized by the blue bar, the red bar, the green bar, and the purple bar, respectively. And here the goal was to understand the enzyme activity on each individual day and make sure that it's relatively stable for the 4 days that BMS wanted to do some clearance studies on. And you can see that they assayed for a variety of CYPs and other enzymatic enzymes not CYP-mediated like UGT, AO, and FMO. And our cells had all the CYPs functional and were relatively stable over the 4 days that they tested them. This data was corroborated with RNA expression data for the same CYPs at the same time points. Here we included FMO 3, 4, and 5, and you can see that the RNA expression is very robust, and also it exists over the 4 days that they did these assays. This is a preliminary study that we did for slow clearing rank ordering compounds. This is a study we did with Schering-Plough, where they had asked us to try to rank order 7 very low clearing compounds. And as you can see in the right farthest column with the red circle on it, we did a very good job of predicting the clearance in human and actually rank ordering the compounds from the lowest clearing to the highest clearing. I do want to say that there was one outlier, lorazepam, but other than that, the other 6 compounds rank ordered very nicely. This is some characterization data that we've developed for our animal models. From top left to top right, you have dog, rat, and cyno monkey. And what we measure here is the formation of hydroxycoumarin from coumarin, and you can see the really stable function from day 1 all the way out to day 14 in all 3 species. We also did a similar assay for phase 2 metabolism in the animal species. Again, dog, rat, and cyno monkey. And here we're saying for 7-hydroxycoumarin glucuronidated, and you can see again that you have very high and stable function over the 14 customer days. In terms of characterizing our cells, the last thing I'm going to talk about is canaliculi staining. And this we do because having nice, robust canaliculi in any species for hepatocytes is very important. It indicates cell health, cell quality, and the overall ability of the hepatocyte to do one of the many functions that a hepatocyte is supposed to do other than clearing compounds, such as making urea and albumin. This is a good metric for just understanding if you have high-quality functional hepatocytes. These pictures were taken 31 days out in culture, and from left to right we go from human, dog, rat, and our primate products. An area that we've recently gotten into is to try to characterize some pooled human hepatocytes. In this particular case, it's a 5-donor human pooled lot, and you can see that after 14 customer days, we have great morphology on the left, nice good tight junctions, nice clear nuclei, and on the right you can see we have some biocanaliculi staining, which again signals that these cells are very happy and healthy and able to produce bile. Characterizing the 5-donor pooled human lot for the metabolic enzymes. Again, we have 1-hydroxymidazolam formation, dextrofan formation for 2D6, and tolbutamide, 4-hydroxytolbutamide formation for 2C9. And again, you see the very stable function over 14 days. This is a slide where I just wanted to show single versus pooled donor function. So these are the 3 donors that I showed you data on before for single donor, and then the purple bar all the way to the right is the pooled donor. In this specific example, I'm looking at 3A4 activity, and it looks like the pooled hepatocytes have 3 to 4-fold higher activity when compared to single donor lots, and this actually applied to most of the different cytochrome P450s we tested, and we believe that this has a lot to do with engineering pooled lots to really encompass a variety of different human populations. This is a study that BMS did using the pooled hepatocyte product, and what they did was they wanted to compare the single donor lots to pooled donor lots, and if you look at the column all the way on the left, you see the 6 compounds. For example, the first compound is timolol, so the timolol on the top, the data for the timolol on top is a single donor, and then you see the timolol pooled data on the bottom, and we did the same thing for imipramine, antipyrine, clomipramine, diazepam, and ritonavir. And all the way on the column on the right, you can see that using a multiplication factor of 2, all the substrate clearance predictions were in 3-fold of the literature values when using the pooled lot. This is a study that we did with QPS where we wanted to measure the metabolite generating capabilities of our cells. This is all going to be now single donor data. And what you see here in the case of Clarinex, it was a shearing plow compound that was a follow-on drug to Claritin. And in developing that drug, shearing had a very hard time generating the metabolite that was highlighted in blue in the screen here, the 3-hydroxydesloratadine glucuronide. The FDA gave them lots of trouble and asked them to generate the metabolite, and they tried a number of in vivo and in vitro systems, and they could not do it. In the study that I'm showing you here with QPS, we incubated the Clarinex with our cells for 5 consecutive days, and we showed that we could make the metabolite, whereas the microsome and hepatocyte monocultures could not do it. And we believe this is because this is a phase 2 metabolite and also a secondary metabolite, and it probably takes a significant amount of time to develop this specific metabolite. This is a couple of slides. The next couple of slides will be from a study that we generated data with UCB Pharma in Europe. They were very interested in the dog model and how it compares to the human in vivo data. And here you can see a compound lorazepam, where the in vivo human clearance, if you look at the bottom of this slide, in plasma is 1.21 ml per minute per kilogram, and for the dog it's 18.6 ml per minute per kilogram. And in vivo, this is a high clearing compound in dog and a very low clearing compound in human. And when run in our system, in the dog and the human on the left, dog on the right, you can see that on the left it takes 7 days just to get 66% clearance of the parent, and when it comes to the dog on the right, after 4 hours you're over 80% clear. So this was a good in vivo, in vitro qualitative correlation to what happens in the actual animal species themselves. The next compound I'm going to talk about is ketoprofen. In this compound, the clearance rates are relatively similar for the 2 different species. So the plasma clearance for the human is 1.6. The plasma clearance for the dog is 1.19. And if you look at the graphs on top, you can see that it takes the human 7 days to reach 80% clearance and the dog 70%. And again, qualitatively, you see similarities between what goes on in vitro and in vivo. Another interesting thing to note here is that if you look at the metabolites being generated at the 7-day time point, you can see that in the human there is only one major metabolite, which is the high peak in green, and in the dog there are a number of different very prominent metabolites. So this signals interspecies differences in metabolism. This next study I want to talk about was done with a number of principles in mind. The first one is that we wanted to take a compound that was difficult to clear, such as tolbutamide. It's a low-clearing compound, and at the same time find a compound that clears differently in the different species. So in this case, it's metabolized by 2C11 in the rat, 2C9 in the human, 2C41 in the primate, and in the dog it's a very minor metabolite. And if you look at the data in the graph on above, you see that the 4-hydroxytolbutamide is being generated at the 5- and 7-day time points in the rat, the primate, and the human, but in the dog it's a very minor metabolite, and again a nice corroboration of what goes on in vivo. The next two slides are going to talk about a study that we did with in partnership with Sanofi, where one of their goals was to look at the CYP contribution to clearance of compounds, of low-clearing compounds especially, where you would want to inhibit a certain CYP like 3A4 or 2D6, add your compound of interest, and try to understand if it is those CYPs that are contributing to the metabolism, and if so, how much they are contributing to the metabolism. So in this case, we're going to talk about 3A4, and we tried a bunch of different inhibitors. We tried ketoconazole, which is a CYP3A4 inhibitor, azamulene, which is another CYP3A4 inhibitor, aminobenzotriazole, which is a all-CYP inhibitor and inhibits most of the CYPs that we see, and then quinidine, which is a 2D6 inhibitor. So as one might think, the quinidine and the control should not inhibit, and that's actually what you see in the blue and gold lines. And you can see that the 1-hydroxymidazolam is being formed, which indicates that the CYP3A4 is very active. And when you add the ketoconazole or azamulene or ABT, which is all these lines grouped and clumped at the bottom, there is no CYP3A4 function for 7 straight days. This is a similar example with 2D6, where quinidine and aminobenzotriazole are clumped on the bottom here, and you can see that they have no function, 2D6 function, and the ketoconazole, azamulene, and the 1% DMSO control all have dextrofan generation and are clearing very nicely. This next set of slides is going to talk about time and concentration dependent inhibition and induction, and what we're really trying to measure is, number one, can we induce and also inhibit our CYPs, and at the same time can we then remove the inducer or the inhibitor and monitor the recovery of the cell to its baseline function. This first example is with ketoconazole. Ketoconazole is a CYP3A4 competitive inhibitor. It's a very potent inhibitor, and that means that immediately upon incubation with the compound you should see a inhibition of the compound, and that's exactly what we saw. If you pay attention to the blue line on the bottom, you can see that it's a very concentration-dependent inhibition. We then incubate for 3 straight days with the ketoconazole, and again the red line signifies another concentration-dependent inhibition. Then you remove the compound from the ketoconazole from the media, replace with fresh media, come back 24 hours later. That would be the purple line with 24-hour recovery. You can see it kind of jumps up a little bit, almost looks like there's a little bit of an inducing effect. But by 72 hours, the cells have completely recovered their 3A4 function and are at 100% of their day 1 function. We then repeated this in the graph on the right with a different donor, where you don't see that 24-hour kind of jump in induction, but you do see very nice recovery back to 100%. The next compound I want to talk about in terms of inhibition is diltiazem. This is different than the ketoconazole because it's a time-dependent inhibitor, and it actually takes time to form. So at time 0, if you're looking at the graph on the right, at the 0-hour incubation, there is no inhibition at all. Incubate with diltiazem for 3 days, and what you see is this really nice concentration-dependent inhibition, signified by the red line. You then remove the diltiazem monitor for 24 hours of recovery. You see it starts to come back up in the form of the purple line, and after 72 hours it actually looks like we have this very, very robust induction effect where the line just goes off the chart to the top. We thought that this may be a fluke or some scientific error. We repeated it in a different donor in a different experiment, and we got the same exact result. And we will be looking to this in the future to try to understand what's behind this severe induction effect that occurs after 72 hours in the absence of diltiazem. The last slide I'm going to talk about in this set of slides is actually an induction through rifampin. It's a CYP3A4 inducer through PXR activation. It's a very strong inducer. And what you can see from the graph on the left is at 0 hours of incubation, so at time 0 you have no induction effect. It's the blue line. Incubate for 72 hours with rifampin, and you see that you're about 200 twofold induction. Remove the compound, let the cells recover for 24 hours in the absence of compound, and now you see a 300-fold, a threefold induction effect, which is very interesting. So even in the absence of rifampin, you're still seeing an induction effect. Monitor the compound, the cells again for 72 hours after you remove the compound, and that's the light blue line, and you can see that there's a very dose-dependent return to normal, or 100% of day 1 function. And after 120 hours of recovery, that's the gold line at the bottom, you see it almost overlaps the day 0 initial starting function of the 3A4. And again, we repeated this in two donors. So that was the bulk of our DMPK data, and next I'm going to get into some of our toxicology data and using HµREL to predict in vitro toxicity for long-term and repeat dosing experiments. So the first slide I'm going to talk about is an early on study that we did, proof of concept study, where we compared the HµREL human to HepG2s, which was the incumbent model in Sanofi, in Schering-Plough at the time. Excuse me. And what you can see is that there are two different types of toxicity or shifts in the TC50 curve here, and that is mostly due to understanding whether it's the parent or its metabolite that's toxic. So because our cell system is robust, it tends to clear parents faster and form more metabolites faster. So in the case of flutamide and ketoconazole, which are the two left graphs, you would see that the parent and where it's thought that the parent is toxic, you see a shift of the TC50 curves to the right, meaning that where the cells are clearing the toxic parent faster, and that means that it takes longer for the toxicity to form. And for troglydzone, where it's thought that the metabolism is mediated by a metabolite of troglydzone, and these cells are robust and they're making more metabolites faster, the TC50 curve shifts to the left, and we see toxicity faster. In the next slide, we just wanted to rank order toxicity, pick about 10 compounds from doxorubicin to caffeine, and just try to rank order their toxicity. And you can see from the graph that we did a pretty good job at just rank ordering the toxicity in the human system, with doxorubicin being the most toxic and caffeine the least toxic. This is a snapshot of a study that we did with a major pharma on 11 compounds. 8 of them were blinded. And the conclusion was that HµREL outperforms the 2 incumbent models, and there were no false positives. The incumbent models that we're talking about here are a high-content screen that was at the time done with HepG2s, and then also ATP, assaying for ATP and HepG2s. And if you just want to pay attention to one compound here, compound G, you can see that it is in vivo toxic. The HCS did not predict it, signified by the 0, and the ATP-HµREL prediction did predict it. The next study I'm going to talk about is a rather large study that we did with UCB Pharma. This is a study where we wanted to use the dog as a predictor of human toxicity. We evaluated over 50 compounds in this study, 35 of them human hepatotoxic, 6 of them systemic toxic, and 10 non-toxic compounds. And again, they compared this to their incumbent models, which were HepG2s and primary human hepatocytes freshly isolated in monoculture. And the first thing that we found was its sensitivity, or the rate at which we predict a toxic compound as toxic, was 78%, and that was very much in line with HepG2 and the monoculture human models. But where we really showed a significant increase in being able to help understand the toxicity was in specificity. Specificity is the ability to measure a non-toxic compound or classify a non-toxic compound as non-toxic. So as the specificity goes up, you're generating many less false positives. For the HepG2 system, it was 36%. For the primary hepatic system, it was 45%, and with HµREL, it was 73%. So we were doing a much better job at not generating false positives. And in the end, UCB concluded that the HµREL dog is a promising model for chronic studies in metabolism and hepatotoxicity evaluations. There's much more to say about this data. We published it in Toxicology and Applied Pharmacology in 2014, and the paper is also available for download on our website. The next set of slides I'm going to talk about are a multi-species comparison of repeat dosing of compounds. So there are a bunch of compounds out there where it's very difficult to see the toxicity effects after 24 hours. And with a system like ours, where you can repeat dose and the system can go for 14 or 21 days, you'd want to try some repeat dosing studies in different species. So here we're going to talk about cyclophosphamide. If you pay attention just to the top left graph, that's the human, and you see that after 2 days of treatment, which is the black line on top, there is very little toxicity except at the highest concentrations. But as you repeat dose on day 4 and day 6, you see the curves shift to the left, and toxicity is visible at lower concentrations. Now this applies across all the species. You have the dog in the top right, primate in the bottom left and right, and the rat in the bottom right. And you can see that there are significant shifts from even 4 to 6 days in the primate and the rat cultures. If you take a step back and just look at one time point, in this case we're going to look at the day 6 toxicity for 2 different compounds. Citroglitazone on the left, where all of the species tend to clump and show similar toxicity profiles, all in the range of an IC50 of 2 to 300. And on the right you see cyclophosphamide, which actually groups into 2 groups, and you have the human and the dog kind of showing less toxicity, and the monkey and the rat showing more toxicity at lower concentrations. So the monkey and the rat are in the range of 1,500 to 2,000 micromolar, and the human and the dog are more in the range of 5,000 to 7,000 micromolar. The next couple of slides I'm going to talk about are part of a larger study that we're doing with Sanofi. The overall study is going to test over 30 compounds in our systems, and again, it's a repeat dosing study. We'll be monitoring cells at 24 hours, 7 days, and 14 days. The cells are dosed every 2 days for that time period. The first slide I'm going to show you is acetaminophen toxicity, and you can see from all 3 graphs really that in 24 hours it's very difficult to see toxicity profiles until you get to the highest concentrations. And if you look at 7-day and 14-day treatment, you see that the toxicity forms a lot earlier on in the process, and that brings the TC50s down significantly. If you're looking at just the TC50 values of the human, at 24 hours you would think that the TC50 is greater than 40,000 micromolar, but as you move on to the 14 and 17 day, it's much closer to 7 and 5,000 micromolar. And you see similar effects in the other species that we tested, the rat and the dog. The next compound I want to just give a quick snapshot of is cyclophosphamide. This is a moderately toxic compound, and it's known to take time to take its toxicity effects. And again, you can see from the human, rat, and dog data that at 24 hours of treatment, you really wouldn't see much toxicity at all. But if you're treating for 7 and 14 days, you see that the TC50 curves shift significantly to the left, especially in the case of the rat, where you see an even more significant shift from day 7 to day 14. This is the cyclophosphamide data plotted in a different way. if you wanted to understand the species-specific differences in the plots or in the toxicity, you'd want to plot each species on a specific day. So here we have 24-hour, 7-day, and 14-day graphs with human in red, rat in blue, and dog in green. And you can see from the 7 and 14-day data that there are species-specific differences in the TC50 values. And if you wanted to use this data to try to understand what would happen in a human, you'd probably want to pick the rat in vivo model to try to model your human in vitro data on. The last compound I'm going to talk about in terms of generating toxicity profiles is troglitazone. Again, you see a very species-specific toxicity at day 14. This is a compound that was removed from the market in 2000. And at day 14, you can see that the human separates itself, the red line separates itself from the green and the blue. And had they had this system available back when they were developing the compound, it might have saved them a lot of time, headache, and money just to understand toxicity profiles like this. Distinction between compounds in the same class is also an important topic of conversation. What we want to show here is that the troglitazone and rosiglitazone, which were marketed for the same purpose, and it's an anti-diabetic, and the rosiglitazone is not toxic at all, while the troglitazone is very toxic. And you can see that if you run both of these compounds in the HµREL system, it very much compares to what goes on in vivo. The TC50 over Cmax for the troglitazone is 7, whereas for the rosiglitazone it's 327. So the system did a very good job of distinguishing between compounds in the same class, one being toxic and one not. To summarize this first set of compounds that were run with Sanofi, this is a table. I just want to point to a lot of data. I'm not going to be able to absorb all of it in the time frame that we have. If you just look at the human in the light gray in the middle, you can see that for the two most hepatotoxic compounds, troglitazone and diclofenac, you have a increasing toxicity over time, and that these systems did a very good job of predicting that. The next set of slides I'm going to talk about in the toxicity realm of things is HµREL Human on a platform designed by ASEO Biosciences for real-time hepatotoxicity monitoring. The ASEO platform is a well plate, regular 96 well plate with embedded microelectrode arrays fabricated directly into the wells. These arrays then measure impedance of the cells, the impedance that the cells cause, and then the lack thereof if the cells are toxic. So you can see in the middle figure here, these are electrodes without cells. The bright gold is the electrodes. The darker color gold is where the cells would be seated. And then impedance measurements are taken from the system anywhere from every minute to every hour to 24 hours. This is the real-time profiling of troglitazone on the ASEO platform, and you can see here that troglitazone is very toxic at its top 3 concentrations. The one thing to notice on these slides is that whereas usually the x-axis is a depiction of concentration, here we're depicting time. And concentration is really the different color lines on the graph. So at the highest concentration, you see toxicity forming very quickly within a couple of hours. For the second highest concentration, it's still a couple of hours, but less than 10. And then at 25 times Cmax, which is the blue line, you see the concentration forming right around, the TC50 forming right around the 12 to 13 hour mark. And this does a very good job of explaining to us at what time point the toxicity occurs, and we don't actually have to kill the cells every time we want to try to assess an endpoint. It also shows that at 12, 6, and 3 times Cmax concentration, so at the lower concentrations, there really is no toxic effect all the way out to over 3 days. This is an example of cyclophosphamide in the ASEO system. And again, here you can see that the different concentrations develop toxicities differently over time. And another thing to notice here is that repeat dosing does matter. And you know, in this case, you would need to dose for at least 2 dosing periods to see a toxic effect. towards the future of the toxicity field, we feel that a lot of the work that's going to go on in the future is going to be geared towards high content analysis and getting multiple endpoints or multiple points of interest from one well to assess both mechanisms of toxicity and being able to do multiple assays in one well and decreasing the amount of wells one might need to assess toxicity. In a collaboration we have going with Sanofi, we are trying to develop assay methods to do this, looking at glutathione levels, reactive oxygen species, and mitochondrial membrane potential. The next set of slides I'm going to talk about really are geared towards the future of HµREL's technology. This is a beta microfluidic device that we have in-house now in our testing. This is really geared towards fluidics and dual chamber applications, multiple tissues. You can see on the figure on the left, that's our patented chip. You can run 3 experiments at the same time, so each one of these 2-chamber units is a unit all onto its own. In the first top chamber, in red, you might want to put hepatocytes, and in the bottom chamber, you might want to put heart, kidney, or lung to assess, number 1, efficacy of a drug, and number 2, toxicity of a drug in conjunction with metabolism, clearance, metabolite formation, and whatnot. On the right, you can see the actual mechanism that the chip fits into, and the circulation all happens under the chip. It's tubeless. It's almost like pushing toothpaste out of a tube with little fingers. Again, this is towards the future. This is a schematic of a 2-tissue microfluidic, one of those little chips that I just showed you in a proof of concept study that we did a little while back. In the one compartment we put a liver, and in the other compartment we put a colon cancer cell line, and exposed this setup to a drug called Tegafor, where the prodrug of Tegafor, which is 5-fluorouracil, is known to kill colon cancer cells. So what should happen is that if there is no liver compartment, the Tegafor does not get converted to the 5-fluorouracil and should not kill the colon cancer cells. And if there is a liver compartment, the colon cancer should die because you're forming the 5-fluorouracil, and that's exactly what happens. In the bars all the way to the left, you can see specifically the red bar. If you have a liver compartment and you're adding Tegafor, you see 65 to 70% toxicity. If there's no liver compartment, which is the set of bars in the middle, you can see if you add the Tegafor, there is almost no toxicity to the cells. To sum up everything I've talked about, what are the advantages of using HµREL? We are a highly stable, reproducible cellular competency. I think most cells per well versus the competition. In a typical 96-well plate, we have 30,000 cells. This leads to higher horsepower, more metabolite formation, better clearance predictions. We also do 384 well, which allows for higher throughput, all shipped to your door. The long endurance and high function enables repeat dosing studies, drug-drug interaction studies, complete metabolite formation, induction, inhibition, really anything that one might think of for the DMPK and tox arenas. At HµREL, we really emphasize lab practicality and convenience. Not only do we want our cells to be of the best quality and produce the best data, but we also want it to be easy for the customer to use. The cells are shipped throughout Western Europe and North America, overnight shipping. The plates arrive ready for use after a brief acclimation period. All the standard formats of plates are available, 384 to 6-well, and all the media is included for ease of use. Put up a slide with our contact information. Again, please let us know if you have any questions, if you'd like a personal presentation, and I hope you've learned something today and generate some interest.
Excellent. Thank you, Dr. Novick, for that wonderful presentation and very insightful overview of HµREL. We have received a few questions from the audience here. First question, have the models been evaluated for transporter function, or do you have any assays?
So yes, we have done some transporter work, in particular in the hepatobiliary clearance arena. So we know that we have functional BSEP transporters, we have functional MRP2 transporters. We've done a little RNA work with other transporters such as OATP and TCP, but we have not done an extensive characterization of all of the transporters, and that is on our list of things to do.
Excellent. Another question, can you talk about the shipping of plates, how they're shipped, and the ease of use of the system?
Sure. The plates are shipped overnight. They're shipped in a regular media formulation with a nice tight seal, so that all you have to do when you get the plates is open the box, warm up the media that comes with the plates, aspirate out the old media, replace it with 100 microliters of the new media in the case of 96 well plates, put it in your incubator for 4 to 24 hours, and start your experiments.
Very good. Can you touch on the robustness of the system when it comes to hepatocytes compared to stromal cells, say compared to other long-term culture models that are on the market today?
Yeah, sure. I think the advantages that we offer in terms of a co-culture is the amount of hepatocytes per well. So I think if you 30,000 hepatocytes in a 96 well plate is pretty powerful. Another thing that we do that I think is important is plating into 384 well plates. And being able to do high throughput analysis with the co-cultures. And in terms of robustness, I think it's got more robustness than anything else you see out there.
Okay. Just give it a couple more seconds here for people in the audience to ask questions. Can you talk, Dr. Novik, about the percentage of stromal cells to hepatocytes?
That's a good question. It's actually part of our proprietary method. So it's difficult for us to say the exact ratio, but I can tell you that there are a lot more hepatocytes than there are stromal cells, and their stromal cells are not enzymatically active, and they do not divide over time.
Very good. Dr. Novik, how long would you say the cells maintain their full complement of enzymes? So if someone was just looking to take the cells out for an extended period of time, how long do you think the system would last?
So we've gone out as far as 21 days, but we have canaliculi staining past that, all the way out to 31 days. But I think in the end, it's if you can find an application that requires more than 21 days, we can provide the robustness to do it.
What types of cells are co-cultured with the hepatocytes, and have you investigated looking at Kupffer cells?
So right now it's just a endothelial stromal cell type, and yes, we will be looking into adding the immune component of Kupffer cells in the future, and it will be on our list of things to do.
Very good. Okay, we'll just give it one more minute here for anyone else in the audience that has any questions to go ahead and type those in. Okay. Well, with that, I would like to one last question here just popped in as I was wrapping up. Dr. Novik, have you looked at any biliary excretion with this model?
So yes, we're beginning to do that now. The data is in very early stages of being prepared, and we should be able to come back with some very exciting data soon.
Wonderful. With that, I would like to take this opportunity to thank everyone for their time that attended the HµREL webinar. I hope you found the overview insightful and informative. We'd be delighted to work with each and every one of you whom are on this call. If you have any questions after the fact, please feel free to email us. We have tons of information on our website as well as posted videos. We'll also post the webinar to our website once we are finalized. Again, if there's anything that comes up, please do let us know, whether it's a service request or request for quote or just questions on the products in general. And with that, I would like to go ahead and thank everyone again, and I hope everyone has a great day. Thank you.